In this video, we're going to talk about the derivative of f as a function, all right? So why don't you pause, copy this first rather dense panel down, and then press play. Previously, we learned how to calculate the derivative of a function f at a given x value like 5 via this hopefully now familiar limit. So that told us the instantaneous rate of change at f at x equals 5. It told us the slope of the tangent line to the graph of f at x equals 5. It told us the slope of the graph of f at x equals 5, all right? So we've had a lot of practice working with that. Now, if I calculate f prime of 5 like this, I can crank out an answer probably. And then if the next question is, hey, calculate f prime of 2, well, then I'd have to set up an entirely new limit just like this with a 2 instead of a 5 and crank it out again. And that'd be very time consuming. So instead, what we can do to maybe save time if I have to calculate a lot of derivatives is I can compute the derivative of f for any x value via this very familiar looking limit. So this is the derivative of f for any x value. The limit as h approaches 0 of f of x plus h minus f of x all over h. You'll note that it's identical to the limit above, but instead of an actual number 5, I'm leaving a generic variable x in its place. So once I calculate this once, if you want f prime of 5, I just plug 5 into whatever comes out of here. If you want f prime of 2, I plug 2 into whatever comes out of here, okay? So f prime of x is a derivative function, all right? Which outputs the derivative at any input value I provide, as long as it's defined for that input value. All right, now, fortunately or unfortunately, we have a whole host of notation to denote this derivative function, all right? So this is the notation for the derivative function of y equals f of x. I could say f prime of x, remember that apostrophe, we say prime, f prime of x, or since y is equal to f of x, I could say y prime of x. Or I could talk about df divided by dx, and that means the derivative of f with respect to x. Now, what this is getting at is it's identifying with that denominator dx that our independent variable is x. Okay, so our run is based on the variable x in the rise over run equation. This becomes very important in multivariable calc. So those of you who are engineers, you'll eventually take multivariable calc. And in multivariable calc, we have more than one independent variable. So we have to be very clear when we say the derivative. We have to be very clear with which independent variable we're taking the derivative with respect to, okay? Nonetheless, that's a notation. And then I can say d over dx of f of x, and I would read that as the derivative with respect to x of the function f of x. I could also then similarly say dy dx, the derivative of y with respect to x, and then this is just take the derivative with respect to x of f of x. All right, so a whole lot of notation. All of these are exactly the same thing. It's telling you to do this, okay? Now, if I want to then get specific and say, oh, but I actually want the derivative of f at a given x value, x equals a, then I can just use some of these notations. These two should be familiar. This one is the derivative of f with respect to x evaluated at x equals a, and similarly dy dx, that's the derivative of y with respect to x evaluated at x equals a. Okay, so lots of notation all saying, hey, take a derivative. All right, so let's try taking a general derivative. All right, let's try taking a general derivative of a nice happy function, okay? And I'm going to use the limit from the previous panel. Give you a moment to pause, copy that down, press play. All right, so I'm going to calculate f prime of x, and I'll remind you that's the limit as h approaches 0 of f of x plus h minus f of x all over h. So that was on the previous panel. Now I'm going to actually evaluate f of x plus h and f of x. Just throw in my denominator. And I'm going to throw in my f of x first just because it's easy. So there's a subtraction sign. And then in parentheses, because I want subtraction to hit all of f of x, I'm just going to copy in negative 3x squared plus 7x minus 4, okay? So there's my minus f of x. Now, f of x plus h tells me to replace each of these x's with x plus h. So I'd have -3 x plus h squared plus 7, replace the x with x plus h minus 4. Right. So there is the evaluation of f of x plus h minus f of x. Now, direct substitution immediately fails. So I'm going to try and destroy all the parentheses up top, and hopefully eventually an h will cancel. We've seen this game before. So I'm going to FOIL out the x plus h squared, and I might do it up here just to save some space. If I have x plus h times x plus h, I get x squared plus xh plus xh, so plus 2 of the xh's for the outer and the inner of the FOIL, and then h times h is an h squared. Okay, and then I'm going to run a -3 through it on my next line. So running a -3 through, I'd have a -3x squared. I'd have a -6xh when the -3 hit the 2xh, and I'd have a -3h squared. Run the 7 through, so it'd be plus 7x plus 7h minus 4. Run the negative sign through, so negative a -3x squared would be plus 3x squared, -7x, and negative a -4 would be plus 4. All over h. And then if I get the red pen of cancellation Beth, we can start going to town. -3x squared gets killed off by a positive 3x squared. Positive 7x gets killed off by a -7x, and a -4 gets killed off by a positive 4. So I think the only survivors are those two and that, right? And if you note, the -6xh, the -3h squared, and the positive 7h all have an h in common. So I'm going to factor an h to the front in my next step. I'm going to factor an h to the front. That would leave behind a -6x for that term, a -3 and one of the h's, and then positive 7h would just become a positive 7 after I factor the h to the front. Right? And since we factor that h to the front, we clearly see that the h on top can now cancel with the h downstairs. And once the h downstairs is gone, I can do direct substitution and replace h with 0. So I get -6x minus 3 times 0 plus 7, which tidies up to f prime of x is equal to -6h plus 7. Okay. All right. And now if I need the derivative at 5, I can simply plug in x equals 5. If I need the derivative at 2, I can simply plug in x equals 2. Right? So I now have a Swiss Army knife that tells me the derivative at any x value for this polynomial. All right. So why don't you pause, copy this guy down. So I have a two-part function. I first want to calculate the derivative of g of t, which is equal to 1 divided by t. And then once I've done that, I want to determine the equation of a line tangent to the graph of g at t equals 1. Okay. All right. So let me start with part A. And I'm going to use that limit definition from the first panel again. Take the limit as h approaches 0 of g of, now instead of x plus h, I'm going to use t plus h because t is my independent variable. So it'd be t plus h minus g of t all over h. Okay. All right. Because I'm trying to conserve some space, I'm going to keep going on this horizontal. H approaches 0. Got my denominator. I'm going to do the minus g of t first because that's easy. So minus g of t is simply a 1 over t. I could put parentheses around there, but there's no need since there's only one term in g of t. There's nothing for the minus sign to push through like in the previous example. Now, g of t plus h tells me to replace the t with a t plus h. Okay, so there's g of t plus h, 1 over t plus h. All right, now, same old problem. Can't plug in h equals 0. Direct substitution fails. So I got to do some algebra to try and tidy this thing up. And the only thing I can think to do is to combine the two fractions in the numerator. To do so, I need a common denominator. So with red, I'm going to insert the common denominator. I'm going to take the product of t plus h times t to be my common denominator. So this first fraction downstairs, it needs to be multiplied by a t. And whatever I do to the denominator, I must do the exact same thing to the numerator. The second fraction needs to have multiplication by t plus h in the denominator to get our common denominator. And then whatever I do to the denominator, I must do the numerator. Okay. All right. So let's see what that looks like. So the first fraction is now t over, I'm going to put the little t first in the parentheses second. So t times t plus h is my new common denominator. Okay. That's the first fraction minus the second fraction is t plus h up top all over t times t plus h all over h. Okay. All right, so now they have the same denominator. I'm going to mush them together and subtract the numerator. So I'm going to have t minus the quantity t plus h. So let's see, this would be the limit. H approaches 0. I've got that h in my denominator. And then this new thing up top is a single fraction now, t times t plus h. And I have my first numerator, t, minus my second numerator, t plus h. And since that minus sign needs to impact the entirety of the second numerator, I put in parentheses, okay? All right, well, and let's just run that through, run the minus sign through to destroy the parentheses. So it had t minus t and then minus h. And I think I see the t's cancel, right? All right, so let's see what happens down here. I think I've got a negative h left in my very top numerator. Then I've got my common denominator, and that's all divided by h, okay? All right, well, something nice happens here. Dividing by h is the same as multiplying by 1 over h. So I took this fraction, and dividing by h was the same as the fraction being multiplied by 1 over h. And that's really nice because now I see an h and an h cancel. So I have limit h approaches 0, negative 1 on top, t plus h downstairs. Okay? And I've killed off the h that was preventing direct substitution, so I'll now try direct substitution, replacing h with 0. So I'd have t plus 0. T plus 0 is just t, so I have t times t. So I think I have negative 1 over t squared. Okay. All right, so my derivative, g prime of t, is negative 1 divided by t squared. Okay. All right, so now I can get the derivative at any t value I like. Well, part B needs the equation of the line tangent to the graph of g at t equals 1, okay? So for an equation of a line, I need a point on the line. Now, we've talked about this before. The tangent line and the graph of g share one point in common, and that's the point at t equals 1. So I'm going to do 1, g of 1. Not g prime 1, g of 1. I want the y value. Okay. So that would be 1. And g of 1 would be 1 divided by 1. 1 divided by 1. So I have the point 1 comma 1. Okay. So there's the point on my tangent line. I also need the slope. So my slope is my derivative. And I'm after my derivative at a particular x value, x equals 1. So I'm going to plug x equals 1 into my derivative. So that would give me a negative 1 over 1 squared, which is a negative 1. So my tangent line has a slope of negative 1, and it passes through the point 1 comma 1. So I can do the point slope form. So the equation of my tangent line would be y minus my y value equals my slope times x minus my x value of the point on the line. So there is the equation of my tangent line. I prefer mx plus b form, so if I do a little bit more algebra, I think I get a negative x plus a 1, and then I'm going to add 1 to both sides. So I think my equation of my tangent line is negative x plus 2.